Yeah, so this is the last paper of this session. So the presenter is Amar. Amar is a fifth-year PhD student at UAUC, advised by Professor Radhika Mittal. His research interests include network resource management and congestion control. He'll be presenting his work on enabling efficient and policy-rich rate enforcement on the internet. Thank you.
Thanks for the introduction, Lee. Hello, folks. I'm Amar, and I'll be presenting our work on enabling efficient policy-rich rate enforcement with phantom queues. This is a joint collaboration with Pratish, Elias, and Mike from Microsoft Research, and Radhika, my advisor from UIUC. All right. So rate enforcement or artificial rate limiting is common on today's networks. ISPs rate limit users to their subscribed rates. Cellular service providers rate limit bandwidth-hungry video traffic to manage limited radio resources. And it is also a common tool to actuate traffic engineering decisions in data centers and WANs. So network operators have following expectations from rate enforcement. First of all, you want your rate enforcement to be correct. So small fluctuations over smaller timescales are okay as long as they average out to correct rate over longer timescales. However, very large bursts, sometimes orders of magnitudes larger than the desired rate, are unacceptable. Operators also desire to implement different rate sharing policies within the enforced rate. For example, they may want to divide the rate R across occupying floors fairly. Other policies include weighted fairness and prioritization. Lastly, we want to do this at a low cost so that we can scale to a large number of users, which is typical of ISPs and cellular service providers. So we want a solution that is computationally efficient, as well as it can support different policies and do that correctly. So let's look at existing mechanisms and how well do they meet these expectations. So we have two mechanisms, traffic shapers and traffic policers. Shapers buffer packet in queues and then dequeue them at the desired rate. And they are quite good at rate enforcement, like they're very precise, and they also allow you to support different scheduling policies. Policers, on the other hand, drop packet exceeding the desired rate without buffering them. So policers are very efficient to implement, but they lack support for policies, and also the rate enforcement is a bit off. Let's go into a bit more details one by one to understand these pros and cons. So we'll start with traffic shapers. Traffic shapers work by buffering incoming packets into queues, and then they dequeue them over time at the rate that you want to enforce. And it is easy to reason about policies with shapers because we can have multiple queues, and we can put packets in multiple queues and divide the rate R across them using any policy. For example, we can do round robin for fairness, or similarly, we can also do prioritization. But even though they can support these policies, they are inefficient to implement. So here is what pipeline looks like for Shaper when implemented in software. So you have two routines. On NQ, you want to classify incoming packets into shapers and queues. So what NIC does is, modern NICs, copy the packets directly into the lower level cache of CPU, where CPU is able to access them and do this processing very quickly. It consumes only 30 CPU cycles per packet on average. But the dequeue routine, where Shaper needs to then prepare a batch of packets to dequeue from all the shapers, that takes place quite a bit time after the packet had come in. So by that time, the packet is no longer in the cache, and it needs to be fetched from the main memory. And this is the slow part of the Shaper pipeline, and it consumes roughly 300 CPU cycles per packet. So now let's go to traffic policers. So traffic policers today are usually implemented using what are called token buckets, where you have a bucket where you're adding tokens at the rate of R. This is just a counter, fancy visualization, but it's just a counter. And incoming packets must consume a token to be transmitted. And if there are no tokens, then you drop the packet. And policers do not need a dequeue routine. They make the decision about dropping or transmitting packet right at the time of NQ. So They're quite fast and consume 30 CPU cycles altogether. But they have their own drawbacks. Firstly, they are very difficult to configure. You can choose one, essentially, you have to choose one. Either they will under-enforce the average rate, where let's say you wanted to enforce a rate of 10 Mbps, they will the flow will actually achieve 7.5 or something. But if you try to fix that, then they will result in very large bursts, sometimes 20 times what you're trying to enforce. And there is, with traditional polycer, there is no way to get to address both of them simultaneously, both these issues. The other issue is they lack policies. Recent work called Fair Polycer presented a point solution to make token buckets fair. It does so by dividing the token bucket capacity fairly between active flows, but it does not generalize to other policies that I discussed earlier, like weighted fairness or prioritization. So in this paper, we asked the question, can we get a rate enforcement mechanism that is effective, policy-rich, and efficient? And our answer is yes. We present BCPQP, which stands for Burst Controlled Phantom Queue Polycer. It allows you to support different policies, fairness, prioritization, and all the other policies I've mentioned so far. And it does burst-free and correct rate enforcement, where burst is controlled, actually. And it does all this at efficiency comparable to a policer and 7 times better than a shaper. Okay, so I'll divide my talk into 2 components. We make 2 contributions. Firstly, we enrich the policer with, we enable policy richness in a policer. I'll go over this. And then also we ensure correct rate enforcement without avoiding any bursts. Okay, I'll go over how we enable policy richness first. So we take token buckets, we saw how efficient they were, and we're gonna re-implement them as what are called phantom queues. So phantom queue is a byte counter that simulates a real queue. They've been proposed in past as an active queue management mechanism, and we here use them for policy-rich rate enforcement. Okay. So real packets are never stored in a phantom queue. In fact, when a packet comes in, it is immediately transmitted, and we enqueue a phantom packet in the phantom queue, which just translates into incrementing the byte counter. And if the phantom queue is full, then we drop the incoming packet. And then again, we dequeue the phantom queue. Phantom queue is dequeued at rate R instead of the real queue. And we're only dequeuing phantom packets. The real packet was transmitted long time ago. And now, similar to shaper queues, it is very easy to reason about policy with phantom queues. You can have multiple phantom queues and then divide the rate R across them using the same sharing policy that you would have done with the shaper. For example, again, you can do round robin between them. Okay, so we call such a system phantom queue polycer, with multiple queues and dividing rate sharing. So there is, while they look similar, there is a very fundamental difference between the two, right? If a packet is coming in at time TE, the enqueue time is TE, with phantom queue, the packet is immediately transmitted, the real packet, the phantom packet is placed in the queue. So the dequeue time is also TE for PQP. For a shaper, on the other side, you enqueue the packet and then dequeue it some D time later, right? And this is the phantom packet in the PQP system would also be dequeued at the same time, TE plus D. So this has 2 implications. Firstly, we don't need a dequeue routine, which we saw results in high efficiency. But the other issue is that this discrepancy in dequeue time for real packet and phantom packet, it translates into error in rate and policy enforcement, but that error is bounded. So in this talk, I'll go over the case for a single phantom queue, but you can find details, more details in the paper. So let's say my phantom queue is sized P, B bytes. Then over any time window delta T, if my phantom queue occupancy does not go to 0, which means that we don't, so over any time window delta T, if my phantom queue occupancy does not go to 0, which means I'm not wasting any dequeue opportunity, then the rate enforced over delta T window is given by this equation, where r plus minus p over delta t, where b is the size of phantom q. Okay, so while the error is like larger on very small time scales, as you increase this time window, what it means is that your enforced rate becomes more and more precise. Like essentially error amortizes over like larger time window. So here is, for example, behavior of a Reno flow, like the variation in behavior of Reno flow over, like it's bounded within this limit. And like this B, which is the phantom Q size, it firstly determines how large the burst would be, like a large B would result in larger bursts. But also there is a hidden implication where a small b can result in under enforcement of rate. And also, so far we were talking about single phantom Q. If you have n phantom Qs, then this error scales by n. So it's quite evident that how we size this b is like really important, like how you size phantom Qs is kind of important. So how do we size them? Should we size them by BDP, where BDP is bandwidth delay product? Like conventional wisdom for shaper Qs is that you should size them at least BDP. So let's see how that works for phantom Q. So I have a phantom Q enforcing 10 Mbps, and like we sized it according to BDP, and we run a Reno flow through it, and we see that it, like if you like average out these these triangles of like Reno, the average enforced rate is less than 10 Mbps. So what is going on here? We can see phantom Q occupancy over time, and we see that it goes to 0 like quite often. Okay, what's happening here? We can investigate by looking at like these sawtooths in a bit more detail. So essentially, as soon as like BDP sized Q is not big enough, as soon as the flows rate exceeds 10 Mbps, phantom Q becomes full, and we drop a packet, and then Reno ends up like halving its congestion window, so its sending rate like halves, and then it takes some time, like it's doing additive increases, so it takes some time to go to 10 Mbps again, and this results in this underutilization. To fix this, we need to let Reno overshoot the 10 Mbps a little bit, so that the overshoot kind of balances out the undershoot. So we need the phantom Q to be sized at least the area of this shaded figure. And once you do calculations, this comes out to be order of BDP square instead of simple BTP. So indeed, when we size it this way, the phantom Q is not going 0 anymore, and that translates into correct rate, right? Like on average, now we have good rate enforcement. But this also has a like bad outcome, which is that we have burst up to 20 times, which is not good, which is a no-no. Okay, so I discussed Reno here, but like this problem exists with other commonly deployed AIMD style protocols like Cubic as well. Okay, so far we've seen how we can use phantom Qs to do policy enforcement with Policer, and we also discussed briefly rate enforcement guarantees and how we should size the phantom Qs. Now we'll briefly discuss the burst control part. Okay. So we can revisit this graph, and like I can try to give you intuition of the burst control mechanism. So first thing is that burst only occurs when phantom Q is empty, and our flows are kind of in a slow start, like exponential growth phase, or like bandwidth. They're doing bandwidth probing similar to what BBR does. That's the case when this burst happens. Once the phantom Q becomes full, and the flow goes in the steady state, then our behavior is normal. Like it's normal across other congestion control protocols as well by design. So, so what we do is we monitor the incoming rate of the flows, like we monitor the incoming rate of the traffic, and then we set like a safe rate thresholds, as in if my flows rate is within this safe rate threshold, we don't need to do intervention. But when it exceeds this safe rate, then what we do is we we fill the phantom queue up with what we call magic packets. So now phantom queue becomes full. This forces the flow to reduce, like the flow's rate automatically comes down below, at or below R. And this like addresses like the burst problem. And we remove these magic packets once the flow kind of stops sending data or it comes below this safe rate threshold. Okay, so yeah, so what our burst control mechanism helps us achieve is that we do correct rate enforcement because we size the phantom queues very large, but we have this magic packet bit which ensures that we also don't cause any bursts. So I've discussed how we can do policy-rich rate enforcement with the policer, and I also showed you how we can, with our burst control mechanism, we can ensure that rate enforcement is correct and burst-free. All right, so we implement BCPQP and other baselines using Intel's DPDK in VMs, Azure VMs. We also run two other VMs, one running a TCP server, another generates TCP flows with, and we route them through this middle box. For our flows, we use different congestion control protocols, Reno, Cubic, BBR, Vegas, and different RTTs as well. And our flow sizes range from 10 kilobytes to 100 megabytes. And in the middle box VM, we're doing rate enforcement using Shaper, Policer, and BCPQP from rates ranging from 1.5 up to 200 Mbps. And the policy that we're trying to implement is fairness whenever possible. And we measure CPU cycles per packet in the middle box VM and measure per flow throughput on the receiver VM. All right, let's first see rate enforcement, how well we're doing there. So we measure CDF of per flow throughput over 250 millisecond windows, and then we normalize it by the rate that we're trying to enforce. The left plot will show you the average rate enforcement, and closer we are to this dotted line, the better. And the right one shows burst, and smaller the tail is, it will be better. So Shaper, as you can see, is very close to this middle line, which is expected. It does very precise rate enforcement. Also, burst is very small. But a BDP square size policer has a very large burst, up to 20 times. But its rate enforcement is correct, even though it's a bit spread out. Once you kind of average it, like it's correct. But a BDP-sized policer, while it doesn't have burst, as you can see for the red line, its rate enforcement is, it's under enforcing rate. You will see that it's a bit shifted towards me. So BCPQP does correct rate enforcement, like similar to BDP square-sized policer, but it also doesn't have a burst similar to BDP, just BDP-sized policer. For policy enforcement, we're showing here like fairness results. We, again, like over 250 millisecond windows, we measure fairness index, and we plot the CDF here. The arrow shows like where things are better. And you can see the Shaper is doing really well, whereas Policer, because it doesn't support policies, it's not. And you can see BCPQP supports fairness very similar to Shaper. I already discussed that Shaper is like very inefficient, very inefficient. The red line is for Policer, and you can see BCPQP has kind of efficiency comparable to the Policer. So you can find more other results in the paper. I'll skip them for now. I'll jump to conclusion. So what I've shown you is that with BCPQP, you can do rate enforcement that is correct, policy-rich, and efficient simultaneously. And this enables a few things. We've been having interesting discussions about ensuring isolation on the internet. This is like a low-cost solution. At least on the artificial bottlenecks, we can use BCPQP to maybe ensure isolation. Also, ISPs can support user-driven rate-sharing policies, this paper, this poster right behind me also kind of somewhat advocates, with minimal additional cost. And then cellular service providers, data centers, and WAN can do burst-free rate enforcement to manage their limited resources at lower cost, and they also get to implement fine-grained rate-sharing policies. With that, I would like to thank you for listening, and feel free to reach out to me if you want to use BCPQP.
Yeah, Zili from Hong Kong UST. Thanks, Sarma. Very nice talk. Just one quick question. I saw you used a lot of timers in your calculation of the rate, right? So does it require high resolution timers?
Timers in calculation of rates.
Yeah, I saw like you calculate delta t, right, to set
I
a
see, I see.
threshold. So
Yeah,
in that
yeah.
means in DPDK, does it require to have a high resolution timer, or what resolution are you talking about here?
I think I was with TPDK I was using nanosecond, which mostly worked out, but I guess like at very high rate you need more resolution. You're right, but you can like get away with some inaccuracy. I would imagine, yeah.
Hi, Federico De Marchi, Max Planck Institute for Informatics. You have some value at some point that depends on BDP, right?
Sorry?
You have some value at some point that depends on BDP to be set.
Yeah, yeah, yeah.
As an ISP, how would I set a BDP?
Okay, so with polices, you would need to worry about BDP. With PCPQP, you can set phantom queue size to be really large, like without caring about it. Like it has a lower limit but no upper limit. And then what you set is rate thresholds, as in like you can say the rate shouldn't exceed 1.5 times what I'm enforcing. Like you can control the burst. So I think the configuration is much more easier with PCPQP
But
compared to.
what I mean is, how can I predict what my BDP will be for flows that come from different distances? You have a flow come from a satellite network and one come from a
Yeah,
linear
it
fiber
can be
network.
very large. You're right, depending on RTT and rate. But I'm saying like with BCPQP, you don't need to worry about
I see.
that at all.
Okay, thank you.
Hi, Ashwin from IIT Bombay. So, do you have any other comparisons with Shaper, like not just the cycles per packet, like actual performance, like Shaper limiting the performance due to it taking more number of cycles?
I think,
Because,
yeah, so
so
go ahead. Go
just
ahead.
so because it seems like saving like 200 cycles per packet, can it have that much of a difference?
Yeah, so it certainly can, as in like if you, like ISPs are doing this at scale, so they're using many like machines, right, to do this rate enforcement. 7x fewer CPU cycles mean you can process more packets, like 7x more packets per machine. So you're like essentially you're cutting the cost by 7x. Yeah. Does that answer your question?
Yeah, I think it.
Okay.